Welcome to All About Machine Learning, Artificial Intelligence, and Neural Network session. My name is Santosh Srirambatla, and I'll be the presenter for the session today. Today's session will be recorded and available online to review. If you have a question during the session, please select the Ask a Question button, which will allow you to submit a question to me or schedule time with any of our Blue Ridge team members. Artificial intelligence is already part of our everyday lives. It is also the future. The easiest way to think of their relationship, the artificial intelligence, machine learning, and deep learning, is to visualize them as concentric circles. With AI, the idea that came first, the largest, machine learning, which blossomed later, and finally deep learning, which is driving today's AI explosion, fitting inside both. AI has been part of our imaginations and simmering in research labs since a handful of computer scientists rallied around the term at the Dartmouth conferences in 1956 and birthed the field of AI. In the decades since, AI has alternately been heralded as the key to our civilization's brightest future and tossed on technology's trash heap as harebrained notion of overreaching propeller heads. Frankly, until 2012, it was a bit of both. Over the past few years, AI has exploded, and especially since 2015, much of that has to do with the wide availability of GPUs that make parallel processing ever faster, cheaper, and more powerful. It also has to do with the simultaneous one-two punch of practically infinite storage and a flood of data of every stripe, images, text, transaction, mapping data, you name it. This has allowed the AI from something of a bust until 2012 to a boom that has unleashed applications used by hundreds of millions of people every day. AI is really quite broad in scope, and machine learning, which is a part of AI, is just a very small part of it. So based on what we can do right now, you can consider what we do in AI as a very narrow form of AI. Technologies that are able to perform specific tasks as well as or better than humans can be done using narrow AI, but they are very specific, which means there is a lot more to come in the field of AI. Once again, AI, broadly speaking, is the science of making machines smart, right? So it is human intelligence exhibited by machines is how it's defined. It's once again a very broad term for getting computers to perform human tasks, right? The scope of AI is disputed and expanding, over time. Every day, it's got a different definition. The system implemented today are a form of narrow AI, right? A system that can just do a few well-defined things such as recognizing objects, gestures. It can do them as well as humans. Most AI systems involve some sort of machine learning or a deep learning technique, but it also uses other technologies such as natural language processing, speech recognition, etc. So AI is the broader umbrella, and in most cases, AI uses some sort of machine learning technique. Some of the common use cases where AI is used today is object recognition, speech recognition, sound detection, natural language processing, sentiment analysis, uh, and when you get into prediction, that's where you will see that is more traditional machine learning. You also use it for translation between images and even picture restoration, as an example, is where AI is quite extensively used. Now let's talk about how machine learning is different. Um, so machine learning is really a specific methodology within the vast scope of AI. So when you say you're doing machine learning, you're also doing AI, but it's just a very narrow. Once again, it's the narrow AI that we talked about. That is machine learning today. And machine learning, it has got a very specific definition to it. It's all about teaching computers, feeding them data, and teaching computers to identify patterns from within the data. as opposed to, computer programming is you define specific business rules or logic to do a certain task. In machine learning, all you're doing is you're passing data, and you're letting the computer decide the patterns from the data. And once the model is trained, you're using that model to make predictions for the data that it has not seen before. So let's take a very simple example. Um, so, spam detection is one thing that machine learning was extensively used. So, before machine learning was born, if somebody had to build a program to classify emails as spam, then you would write something that is shown here in the traditional programming box. You would say, if email contains a set of words that obviously the spammers would uh, try to bypass over time, and they try to put in special characters and so on and so forth, so you're not looking for those exact keywords. So you would keep adding more and more keywords to your programming logic, and that's essentially a set of hard-coded occurrences of these, right? This is obviously not scalable. Now if you know look at it in terms of how you implement this in machine learning, you're passing all the emails, every email that was classified as spam. um, you know the the machine learning model is learning based on the keywords that are in that. It's determining patterns, and any new email that comes, it's automatically able to tell you based on the existence of certain keywords that it is used in the past. Based on the occurrences, based on the ranking, it's able to use that and say this new email should also be considered a spam, right? So if you look at the definition once again, a machine learning model at a high level, it takes some data, you have to feed it some data to train the system. It learns the patterns from the data, and then you can ask the model, the machine, to make predictions on the data that it has not seen before. Now, let's see where machine learning can be applied with another example. So, a bank is interested in identifying customers at risk for for churn, right? So they have, of course, at their disposal tons of data of the past and present customers um, who have churned versus not churned. So if you look at the data that is pulled here, um, they have the age of the customer, the gender, the number of dependents, if the customer is self-employed, salaried, even retired here, and other transactional information like what is their current balance and so on and so forth. So right, so they have all of this information with them, and these columns, all these columns except that column that's highlighted in green, all these columns are called as features in machine learning. And the output, which is in green, is called the target variable. So this is an example of what we call it as a label data, where you already know the output for the past data, right? You already know if a customer has churned or not. So if you look at it, the machine learning techniques will involve identifying features upfront. So you have identified that age, gender, balance, occupation are all important features for you to be able to determine the if a customer would churn or not, right? It's about identifying the features, collecting and extracting the data, analyzing the data, right? You're analyzing each of these features to determine if you're going to keep these features or drop these features, right? So some features, for example, you have the branch code here, it may have no correlation to the churn rate. So in that case, you would drop, branch code as a feature when you're building this model. And you do not want to include too many features also, because that results in overfitting of the model, and it reduces the accuracy of the model for future predictions. So identifying and keeping right features, it comes from experience. That's what data scientist ends up doing, and they use some programming skills, some data visualization techniques, as well as some of the statistical analysis, right? So uh, there are now multiple sets of libraries and packages available to perform this statistical and data visualization analysis to really identify what are the relevant features, which ones are important to keep versus drop, and so on and so forth. So going back to this example, to this feature, we might drop like the branch code, like I mentioned, right? So once the model is trained using this existing data set of customers who have churned or not, you're now able to make a prediction for your existing customers. As a customer we walk into a branch, uh, you are able to make a prediction if this customer is likely to churn or not. So, that was one specific example, but if you kind of consider other machine learning types and techniques, there are three broad types of machine learning techniques out there. The example we saw earlier with the customer churn is a type of supervised learning. So supervised learning is a type of machine learning technique where you're training data, the data that you're passing to the machine learning model for it to uh, derive patterns, that already has the labeled output. So you kind of know if the customer has churned or not, right? So that is basically the difference between supervised learning and unsupervised learning. And within supervised learning, there are two types as well. One is regression and the other is classification. And truly depends on your target variable or your target output. If it's a continuous, it's kind of like a, a decimal that you're trying to predict, like for example, price elasticity or a forecast, then it would be a regression problem. But if it is not a number, in this case, the example we looked at with the customer churn, it was a yes no, right? So that's more of a binary classification, but you could also have classification into different families and so on and so forth. You look at the unsupervised learning. Unsupervised learning, you don't really have any of the labeled output. So for example, you just have a set of customers or products or suppliers, and you have no prior association or prior definition of how these suppliers are grouped or ranked. And all you have is some business data, some numerical data associated to this data. And you can use the unsupervised learning technique to do what is called as clustering, right? So what this technique will do is it will group all the types of certain suppliers into 3-4 different clusters, if you will, and then you will have to look at them, and you can label them, or you can objectively look at them and see if that association makes sense for you. So some of the examples where clustering is used is you can objectively look at your suppliers or customers based on different data points, and asking the system to group them, right, as opposed to using a predetermined grouping. Sometimes this can be used as a great starting point, and sometimes you would even use this to periodically assess existing groups, right? So you may call your set of some set of suppliers as your A suppliers. Well, is it truly the right grouping, right? You could put it through this clustering model, and it will confirm if you have the right groupings or not. Um, Reinforcement learning is a special type of unsupervised learning. In this case, also you don't have the target variable defined, so you don't have past observations of for the machine learning model to go off of, right? And the reinforcement learning is heavily used in robotics for industrial automation. This is a self-learning model where each correct step is rewarded, and a wrong step, that reward is subtracted. So it's really a self-learning machine learning model. It is quite useful when all you have is a simulation model, and you don't, the only way to collect information about that environment is to interact with it and learn from it. So again, this is something very specific to industrial automation and robotics, probably not relevant for what we do in supply chain. So then, from machine learning, let's talk about deep learning a little bit. So deep learning is one of the one of the special machine learning techniques. It's kind of an advancement of machine learning technique. There are specific use cases where a deep learning method is quite useful, and we'll talk about why deep learning was created and where it makes more sense. So, why was deep learning created, right? So if you think about the traditional machine learning, which we talked about in the last two slides, traditional machine learning requires you to define a set of defined features, right? You have to define all those features, you have to keep the relevant ones, and you have to drop those, right? So these are really hand engineered, and because they are hand engineered, they're often brittle in practice, right? So what happens if you actually didn't even think about adding some features that have high correlation to what you're trying to predict? um, so there is something subjective about the selecting the features, and so that's where deep learning is quite useful. So let's take an example. For example, face recognition. In order to recognize, right, so let's say you have an image and um, you're trying to recognize if there is a face in it, right? And so you have to first determine if that image has mouth, eyes, nose, etc., right? And if you take each of these, let's call them as subcomponents. So let's take the subcomponent of a mouth, right? This is determined, by if there's a pair of lines and in a certain orientation, right? So then you would say there is a mouth in this image. And so if you think about trying to define these as features, the sub features for nose and ears and mouth, going back to how we created features in machine learning technique, it would become extremely complicated, right? And there is a lot of interdependency as well, right? So you have to have the lines for it to be called a mouth, and you have to have a mouth, ear, and nose for it to be called a face. So the definition is almost hierarchical in nature, as opposed to the traditional machine learning technique that we saw, where the features that you're passing are independent of each other. Now, the key idea of deep learning is for the model to self-learn these features from the raw data itself. So what you're going to do is you're going to take a number of these images of faces, for this example, and a deep learning algorithm is going to develop some hierarchical representation internally of detecting the lines and edges in the first level. Using these lines and edges, it will then detect the mid-level features like eyes, mouth, and nose, then composing higher level features like jaw lines, side of the face, etc. And these are all used to determine the final face structure. The fundamentals of deep learning have also existed, for a while, but why, it's really relatively new in terms of it taking off since like 2012, 2015 is when it really took off. And there are three reasons. One is, data availability, large data sets available thanks to all the big tech companies. Data is available everywhere. The second is hardware. Uh, Development of GPUs, especially in a cloud infrastructure. Uh, Basically, you are able to massively parallelize compute at a relatively cheap cost. And finally, because of these, there is a lot more improved software libraries and toolboxes, a lot of them open source, that makes it very easy for people to kind of embrace deep learning. So just taking this a little bit further, uh, deep learning is best suited when the features, right, engineering of the features is difficult. We talked about that, such as image recognition, face recognition, and each one of them, if you really break down the inputs, the images are really, they're all numerical data. There's lots of numbers when you break it down to the pixels. And when you have lots of numbers and continuous stream of numerical data, um, they have patterns in them, and that's what makes it a perfect candidate for deep learning. So if you think about an example that we saw earlier, the way the deep learning model learns is it has a series of inputs. So if you think about it, x1, x2, x3 are three different inputs, and basically what it's going to do is the model using algorithms is going to determine different weights. It's going to determine the weights. It's going to do a product of the weight and the input. It's going to apply a bias. It's going to then apply a non-linear activation function to determine the output. So this is basically based on the different inputs you give. The deep learning algorithm is constantly determining which of these features, x1, x2, x3 internally, again, these are just numbers, which one has a more weight versus less weight, right? And that's how it's automatically able to um, determine the output. And if once you kind of give a new set of numbers, it's quickly able to apply this math to come up with the output. Now this nonlinear function, there's different types of nonlinear functions that you apply, logistics, binary step, rectified linear unit, so on and so forth, for those of you who are keen on understanding the math behind it. um, so the one of the things that we are releasing shortly is neural network forecasting. And Raj is doing a session on science behind um, neural network forecasting. But neural network forecasting is basically a deep learning technique. It uses the 3 years of demand history as inputs to determine the forecast, right? And it is, for fast moving items, it is a perfect candidate. And uh, it is, in the simulations that we've run, it is going to increase the, forecast accuracy. Um, you know, it's going to be quite useful forecasting technique for us. Now, so think about, we'll talk a little bit about AI, machine learning, deep learning, and so the question comes to what can each of you take away from this, and how can you apply some of these principles, how apply machine learning, AI, deep learning, implement this in your business, right? And there are really many areas you can apply these concepts in, like examples we looked at. But what makes sense for you is going to be truly be driven by your business objectives, your pain points. And some of the examples I wanted to throw out there that are common, in the master data management, whether it's done as part of a PIM solution, an MDM solution, or even your ERP, um, you could apply some of the clustering techniques to do much better product customer segmentation, like even driving better uh, group hierarchical values for new products as they are being introduced. Let's say you don't have, you have not taken this as a project. You could actually start a project to assign these groups for all products that are unclassified, and you'll get pretty good accuracy, a great starting point to have the product and customer or supplier segmentation done. And another area that I think would be of immense value is to kind of analyze your suppliers uh, from number of inputs, right? So if you look at how you see a supplier's performance, it could be based on quality, it could be based on time to delivery as well as to request. What are they doing in terms of technology responsiveness, their financial information, demographic information, right? There's so many features available, so many data points available from a supplier perspective, and you can do some sort of scorecarding. You can do assessment analysis of your suppliers using some of the machine learning techniques. And you can apply similar thing with customers, right? You can kind of look at who is at risk, who is likely to grow, what kind of new product lines can you offer to these customers that you're not offering to, what kind of discounts can you offer to some customers which may result in more growth, and so on and so forth. So that was it. Thank you for joining me for this session. This concludes the presentation, and I appreciate your attendance today. If you have any questions, you can message me or any Blue Ridge team member by going to the attendee section and selecting the send message option. Thank you again for your attendance, and enjoy the rest of the conference.